Chapter 5, Section 5. As we were going on in this chapter, our complexity of what we're factoring, or patterns that we need to consider while we're factoring, just get to be more and more complex. Well, one of the patterns we did when we were multiplying polynomials was something called a cubed binomial, or the sum of two cubes, or the difference of two cubes, and that's where they start here when they're beginning of this section. They're looking at these two things here. When I have this pattern occurs, usually the result is what we're looking for. We get something that's something cubed plus something cubed, or in this case something cubed minus something cubed. This pattern of how things will distribute and those kinds of things are key to recognizing, since we can go the other way. So if I find something cubed plus something cubed, I can write that as whatever that is cubed plus whatever that is cubed for the second term as an addition here, and then I take that cube portion is squared minus these two multiplied together plus the last term squared, the last part that is cubed, which is a mouthful. So let's look at some examples. There's two of these patterns that we need to recognize to do this type of factoring. Example 1, it says write an equivalent expression by factoring. Remember, factoring means I'm going to write this as a multiplication. So we have x cubed plus 27 right here. Well, what I need to look for is, first of all, when I see two terms, usually what I look for is difference of squares, because that's the easiest one to factor. It's definitely easier than this. And, well, I don't have a difference. There's no opposite signs here, so that doesn't work. And plus x cubed is not something squared. Well, if I can recognize that x cubed is something cubed, or to the third power, and 27 is 3 to the third power, this is a sum of cubes pattern that I can use for factoring. That's this pattern right up here. So it's just like using this as a formula. So I take the things that are cubed, like x and 3, those become my first parts of my factoring, my binomial, x plus 3. And then I take the x and I square it, right? I subtract the multiplication of these two, 3 times x, or x times 3, you get a subtraction of that, or change the sign, and then here you have 3 squared. So when we check this, which you should do all the time, is if I multiply back, I would actually get the original polynomial, x cubed plus 27. So we're looking for basically this pattern to help us with these things. So when I have binomials, or two terms, this is when I look for it. I can have these cube summed or cube differences, and use that pattern to do factoring. Or the next thing, or the other thing that can happen, is difference of squares. So that's example 1. Example 2, I already got a question from a student via email on D here, so I'll spend a little bit of time here for sure, since I got a question. But let's go through these examples. The examples are worth like 1,000 pictures. So we look for that, and basically they're going to give us examples that we can use these patterns to help us factor. So if I have 125x cubed minus y cubed, well, this is pretty obvious. This is something cubed. Not too sure about this. And then I have to say, well, 125, if I prime factor 125, I end up with 5 times 5 times 5, or 5 cubed. So in this case, the thing that is actually cubed is 5x. Remember, we got parentheses around this. This means 5x times 5x times 5x. And if I multiplied that out, I get 125x to the 3 power minus this. So hey, I have a difference of cubes, so I can use that pattern. So I go back, and the first part of it's pretty easy. I use the 5x minus y, and then I square the first term, I add the product of the two terms together, which would be 5x times y. I get 5xy, and I square the last term, y. And then if we check that, we'd find that. Now b, you know, I could factor 64, prime factor, and I'll get 2 to the 6th power, I think it is, or 4 times 4 times 4, which is a perfect cube. But something to the 6th power, I can actually write that as something cubed. It would be 2 to the 2 power all to the 3rd power. Remember, you got to use your power rules and so on. So even prime factoring, I can figure out that 4 is really what I have here, 2 squared. So they use this here, this one, and also it kind of relates to this. This is a nice example to look at. If I prime factored this, I get m to the 6th. If I prime factor 64, I get 2 to the 6th. Well, I'm not looking for perfect 6 or you know, something taken to the 6th power. I'm looking for things that are cubed. So they say, well, m to the 2 power cubed is m to the 6th. And then I could say also 2 to the 2 power to the 3rd power, the entire thing to the 3rd power, is 64. And I'd end up with m squared in here and 2 squared, which is 4. Well, then you fill in your values based on that pattern. Make sure you check and do that. Here's another one here, and the trickier parts too is this. We got to remember, what do we always do when we're factoring? We look for common factors first to make the problem a lot simpler. Usually it's going to decrease the amount of complexity of this problem, you know, by tenfold usually, if you can find a common factor first. And in this case, there is 2y. You know, I can look at these coefficients here, and they're both even. I know 2 goes into them. But I can always catch these things by prime factoring. And if you get good at using prime factoring trees, it doesn't take very long here. And then the other thing is, I got a y, a factor of y here 7 times, and a factor of y 1 time. Well, that means they have a common of 1. So they factor out 2y. And if you multiplied this back, you should get this original. That's how you check that. Even if you're not sure if you got it, or you may have made a mistake, probably the mistake you usually make when you're doing common factors is don't get the biggest one you can get out of there. And that's what you should check here. Well, this number's even, so 2 goes into these, and you know, this is actually a power of 2. This is 2 to the 6th power, so 2 is the only factor of 64, and 125 is 5 to the 3rd power, so there's no common factors there. There's no common variable factors either, so this has no common factors. Then they get here and they say, well, 64 y to the 6th could be written as something cubed as 4y squared all to the 3rd power, or cubed. And if I did this right here, this means 4y squared times 4y squared times 4y squared. If you multiply that out, you're going to get 64y to the 6th power. So using this power of powers is the key to remember how we do powers of powers will help a lot. Well, same thing here. This is 5 cubed x to the 6th. There's that x to the 6th here. Notice if I cube that power of powers means I multiply the exponents. What exponent is on 5 right here? It's actually to the 1 power. So really, when I take power of powers, I take 3 times the exponent of this, which is 3 times 1. I get 5 to the third power, which is 125. So a lot of review that we're going through here on working with common factors, okay? And actually what we're doing is just rewriting these things as a power of a power. And why we do that, again, is to try to find that difference of cubes, because I have a pattern to help me factor that. So once that pattern's there, I know now what my A and B, if I look back at the first part where they define this pattern, I fill them in and I end up with my new factoring here. Now to go. Huh? Get to bed. You need some rest, son. Are you going to be, I'm trying to record a lesson here. Are you going to be quiet? Okay. So the pattern's put in, we get this factoring, and then I should check to make sure that here, make sure this isn't difference of squares, right? This is something squared, but this is not something squared. And then I look for that. If I did catch all my common factors right at the beginning, there should be no common factors here to factor out. Now D does a couple things, and this is really, we want to make sure we factor completely. And if I'm looking for this difference of cubes in this case, I would get r to the third power squared. But they're not doing that, are they? So all of a sudden I stop and I say, hey, this isn't, they could do difference of cubes, but what is an easier thing to factor first? We should always look for difference of squares first. It will save you a lot of headaches if you do this. If you start off looking for difference of cubes in this type of example, it's just like what I talk about in they talk about in all the strategies about factoring, is look for that common factor first. Well, you kind of step down. It's almost like order of operations in the sense that I want to step up in complexity of what I'm going to do for factoring or what I'm looking for. So try to do the simplest things first, like common factors. Then depending on what I have, if I have a binomial, there's two terms here. The easier thing to look for is difference of squares. So we look for that first, and that's the first factoring that they do here. They say, well, hey, this could be difference of squares. This could be r cubed squared minus s cubed squared. That's difference of squared. I can rewrite that now as these two binomials multiplied together, which is r cubed plus s cubed times the quantity r cubed minus s cubed. So now when I have these, I look and say, well, there's no difference of squares I can do here again. There's no common factors, all those kind of things that we should perform first. So then I have a two-term expression here, polynomial. So I have difference of squares that I can look for, and then I have sum of cubes and difference of cubes. Well, we have both of them right here. So they take the sum of cubes right here and they get this portion, these two factors here. R, the quantity r plus s times the quantity r squared minus rs plus s squared. That's the pattern for the sum of cubes. Well, this part right here is the pattern for the difference of cubes. So that's how they got these two parts. And again, if you didn't start out looking for difference of squares, you went off in a completely different direction. And if you are really, really good at factoring, you could get to here. But it would take a lot of skill to be able to determine whether or not we're doing that. And that's exactly what they talk about here. Is suppose we would have done this like I was talking about and said, hey, this is a difference of cubes, and rewrite this thing. Well, we could still get there, right? Almost. We end up, now look at what here's what we got as a complete factoring. Hey, these two things match up here, this r plus s and r minus s. But this r to the fourth, r squared, and so on, is not anything we've had a pattern for. And we'd have a tough time getting any farther with that. And that's what they're pointing to. They're saying that really this is can be factored into these two trinomials, which is very difficult to factor to. In fact, we don't have any shortcuts or anything that we've talked about on dealing with a pattern on this kind of trinomial and so on, because really the factoring this is a trinomial times a trinomial. Tough one. Okay, so the strategy should be look for the easier things first, and hopefully you recognize, hey, I have a difference of squares I can do first, and then my resultant factors we need to make sure and check to see if we can factor them anymore too, right? So in this case we can. So here's all the new factoring facts really. Again, this is not really new information. It's really reversing some of the patterns that we've talked about when we've done multiplication and shortcuts that we've done. And I did say this in prior chapters too. A lot of times we're doing things and they're pointing out patterns because this is coming in the future, is that we're going to need these patterns and be familiar with these patterns to be able to say, hey, oh, I can factor this way. So remember what you're doing here, and we had already had difference of squares, but they give it again. And so strategies again, and before these useful ones that they talk about, which is some of this is repeat, is look for common factors first if you're factoring. If it's a trinomial, look for perfect squared trinomials, and if it's not, then we'll do anti-FOIL, or grouping is another great way to factor trinomials. Grouping is probably the more powerful method. If you get good at that, your factoring times are going to go way down. So when I have those trinomials, that's the options that I have. And then this last section here that I've talked about is that if I have two terms in these three special ways, we actually talked about this one last section. Here's two terms in this special way where I have something squared minus something squared. That's, they call it difference of squares. I can factor it out into this pattern. The two new ones are right here. When I have a sum of cubes or a difference of cubes, I have patterns that will help me factor. So good luck with it.